Part 4 in the brief look at the Dottori Kun arcade game hardware, and a chance to look at the Z80 chip and how it can be implemented in Verilog on the MiSTer. In this short video, I'd like to go over how the Z80 clock is created, and how it allows the arcade board to alternate between access to the VRAM by both the CPU and the display circuit. As we did last time, let's take a look at the schematic and see what logic chips are being utilized and how. First up, just as last time, we have the 4 MHz input clock that feeds into one side of the IC3 OR gate and the other into the LS14 NOT gate, creating the opposite of the input clock. Moving down, again, the NOT 4 MHz clock feeds into the two LS161 4-bit counter chips, both IC10 and 11 as clock inputs. Out of IC10 we have the 4 MHz divided by 4 and 8 that feeds into the IC4 NOR gate above it in the schematics. The carry or overflow pin of IC10 feeds into the input of IC11. Two outputs, the 4 MHz divided by 128 and by 256, go into counter IC12 and 13. The 4 divided by 256 also feeds into one side of the IC4 OR gate. The 4M divided by 32K and 64K, as before, feed up into the other part of the IC4 NOR gate. And that output of IC4-1 feeds into the other side of the NOR gate we had previously. Output IC4-4 goes up and around to feed into IC7 NAND gate, whose output supplies the D flip-flop of IC9. This low output, the opposite of the VRAM labeled pin, goes round to feed the IC3 or gate which creates the Z80 clock. The other part of the IC9 D flip-flop output goes down into the IC7 NAND gate, and together with IC10 pin 14, which is the 4M divided by 2, creates an active low N load signal from pin 6 of the IC7 chip. Later we'll see how this loads data from the screen memory into the display. Looking at the code for this, we see very similar to the last time. This code here is how we set up the clock input, the 4 MHz clock, and then make the not 4 MHz clock as well. And we're setting up the counter registers and wires. The same code we saw last time creates the counters of IC10, 11, 12 and 13 with the 4 MHz clock divided by 2 all the way up to divided by 65, 536. Now, in addition, we have the IC4 outputs. So we have IC4-1, and that is created by a NOR gate of the 32K and 65K here. Then we have the IC4-4, which is the input from that 4-1 with a NOR gate of the 4M divided by 256. Now that feeds into a D flip-flop. Now the D flip-flop is cleared when we have the clear going low. In this case it's going to be the reset signal. So it changes state on a clock. The clock is the 4M clock. So for the Verilog code we have an always block with the sensitivity of the clock 4M and the negative edge of reset. And so if the reset is low, the output to the VRAM write enable is 0. And the other pin is the opposite of that, so not VRAM write enable is the opposite of the VRAM write enable, and that's constantly always the opposite, so it's outside the always block. And if we don't have the reset enabled, then it's just going to be the state of the input pin, which is the D input pin, is an AND gate between the IC4-4 that we set up here and an OR gate here, or a NOR gate of the 4m divided by 8 ORed with 4m divided by 4, and all of that is in a NAND gate, so hence it's made the opposite with that there. So finally this creates the Z80 clock. This is an OR gate between that not VRAM write enable and the clock 4M. And then under here we have the load signal, which is used by the display circuit to load data from the screen memory onto the display, and that is active if with an AND of the VRAM not VRAM write enable and the IC1014 pin. So from that code I chose a bunch of the wire traces in Model Sim, much as I showed last time. The input of clock 4M is pertinent, as is the not clock 4M. I'm showing some of the divided signals of that as well. And then the main thing is the not VRAM write enable, clock Z80, not load, and then I'm giving that some context with showing the previous sync trace that we had before, because we'll see that's quite interesting with how the Z80 is being slowed down when we're actually wanting to display something on the screen. So while all of those traces are useful, let's limit ourselves to the not VRAM downwards into the sync, and then we can split those traces up just by time scale. What I've done is provided additional magnified versions below those traces, each one just a bit more magnified than the last one. So on the top here, I want to show effectively that this is our VSync, and so between here and here is a single complete screen showing, and what we'll see is that the not load is active at this space between here and here, and so effectively this is the top of the screen. We have some gap, then we have a display, and then another gap before the bottom of the screen. We'll see that the clock Z80 is active all the time, but we'll see as we go down that starts to get modified. So as we go in closer, this now becomes the H sync, so each one of these is a horizontal line, and you can see we have some horizontal lines at the top where we don't have any display, and then now we start to get a horizontal line with some display, which is obviously our game. This is showing it a bit closer in, and we can see it's loading something at regular intervals, and as we can see here, yes indeed, each one of these corresponds to a square in the line, and you'll see how many squares we have in a minute. We'll show how that corresponds to the display on the screen. But this is really the most interesting part here, and this is showing that with all of those logic traces that were being worked out previously, the Z80 clock is going along very stably until we get to this point here, whereby we want to start taking in data to the screen from the screen memory. So what happens is the Z80 is actually halted. You can see it's held high, while during this point the VRAM write enable is able to happen here. Remember, active low, so we can write to the video memory. Here we can't write to the video memory, and the reason is because the video memory is being read, and each time we get this not load is when the video memory is being read for the display purpose. So effectively, not load goes low, the CPU is held and the VRAM memory is not allowed to be written to during these periods. And it does this for 16 squares across in the game. Now let's go and have a look at how that compares to the screen being plotted. So here we've got our screen, and you can see there is some border above, to the sides and below. And so what we can do is if we just shrink that screen just a little bit, and we can superimpose the waveform we had before for the VSync. And so what we'll see is as the plotting goes from VSync low area to low area, we get to go through the not load period, and the not load traces coincide with the arrows plotting the screen area. So that is for the complete vertical signal. Now if we go on to have a look at the horizontal signal, again we have our screen, we can superimpose this time, forward it in, and if we split out the not load signal, we can see how that lines up as we go along, with each line being plotted. Every time we got the not load going low, it triggers picking up some data and putting it into the display. And that happens 16 times for each block of memory. And of course each block is 8 bits wide. So that's what I'm going to cover on this one, just a very quick one, looking at the Z80 clocking and how what we call contention of the VRAM. And so effectively the solution with this hardware is to just stop the Z80 completely when we want to get data from the VRAM. Sometimes there are cleverer ways to do it, but in this one we're just literally stopping the CPU. Now what this does is it takes our effective speed from 4 MHz down to 3 MHz. That's a performance drop that we get during that period of plotting on the screen. Obviously for a game like this, it really doesn't make any difference. Very simple game. But for other games, possibly that could be too much of a hit in terms of performance, and there may be other ways to get around that. Hopefully we'll see that when we look at some other Z80 games on our journey through arcade hardware. So I'll catch you next time, and we will be looking at the Verilog model of the Z80 chip and how it reads and writes data from memory.